Hi, everybody. Today we will discuss something about cross sections and what we call Cavalieri's principle. First things first, with cross sections. Cross sections are, in a way, a lot like when you do in science class and bio, where you do like a cross section of a cell. So it's almost like you're taking a slice of it and seeing it from a different perspective. Now, there's a few ways you can do slices. You can do them horizontally, vertically, at an angle. So there's a few diagrams here that kind of illustrate the different types of cross sections that you can get from these different solids. One comment I would like to make regarding cross sections is that a lot of times the base of the figure has something to do with the type of figure that you get with the cross section. What I mean by that is that taking a cross section, for example, and getting a circle out of it typically requires an object that has a circular or a curved part to it. So you're not going to get a cross section of a circle from a cube or a triangular pyramid. You typically would get those from like a sphere or a cone or a cylinder. So feel free to look those over. I attached a GeoGebra applet there to explore different examples of cross sections. Cavalieri's principle. What it really does is it says that if two figures have the same height and the same cross-sectional area at every level, then the two items have the same volume. So a good example of that would be this example of quarters. So let's say you have 23 quarters. And I think what they're trying to get at here is that if we were to stack 23 quarters perfectly on top of each other, like the example on the left, and let's just say we were to stagger them so that they're not all perfectly even on the right, these two composite figures have the same volume. Why? Well, their cross-section area is the same at every level. So every time you take a cut horizontally, we have the same area. They're all a quarter, and they have the same height. So what does this really show? Well, if we use Cavalieri's principle to find the volume of this oblique prism, this would be very similar then to saying, well, couldn't I draw the figure like this? Make it a right prism with a radius of 2. And now the height being 5 as a standard perpendicular height. So the argument here is that these two figures would have the same exact volume. Okay? So the volume of our cylinder, again, was pi r squared h. So in this case, it would be pi, the radius is 2. We're going to square that, and I'll multiply that by 5. There's no mention of rounding, so 2 squared is 4, times 5 is 20, so I'll leave it as 20 pi. 20 pi, and that'll be cubic inches of volume, is what that cylinder can hold. All right, example 2. The diagram below shows two figures. Figure A is a right triangular prism, and figure B is an oblique triangle prism. The base figure of A has a height of 5 and a length of 8, and the height of prism A is 14. The base of figure B has a height of 8 and a length of 5, and the height is 14. It says use Cavalieri's principle to explain why these two volumes are equal. So I think the idea, what they're trying to get at here is what is the base shape, and that's a triangle, okay? That triangle would be, I'll show in purple in both of these. And I think the objective here is that the area of a triangle is 1/2 base times height. And in figure 1, what is the base of that triangle? The base is 8, and the height is 5. So 8 times 5 is 40, half of that is 20. And then couldn't you argue that the area of the triangle in the other one is really the exact same thing, except this time the base is 5 and the height is 8. So, I mean, they're the same dimensions. We're just flip-flopping them. So what Cavalieri's principle says is that volumes are the same if they have the same base area at every level and the height's the same. Well, what do you notice about the height? The height of each of these is 14. So, Cavalieri's principle. the volumes of the triangular prisms are equal because they have the same cross-sectional base area and have equal heights. And that's essentially what Cavalier's principle is in a nutshell. So what I want your homework to be, and you will get full credit for this, I'd like you to take a picture of something in or outside of your house that models Cavalier's principle. Copy and paste your picture into your one notebook, or you can, I guess, email me, but I prefer you put it in your notebook, and I'll give you a nice grade. All right, try not to use the example that we use with the coins. All right, that one's already been used. Try to be a little bit creative, okay? So here's some extra volume questions for you, okay? Find the volume of each figure. Again, please remember the general formula of volume is capital BH, where B is the area of the base. So in a lot of ways, the first one we already kind of just did. Find the area of the base. The base is the triangle. So the area of the triangle is going to be 1/2. The base is 12. The height is 8. Okay? Half of 12 is 6, times 8 is 48. So that's going to be your area of the triangle. So your volume and then the prism is the area of the base times the height of the prism. Not the height of the triangle, the height of the prism. So we're going to do 48 times 20. Let me open my calculator here. Get that going. All right, so we'll do our 48 times 20, and we're looking at 960. Okay. So 960, and that's a volume now, so that's going to be centimeters cubed. All right, the sphere. We saw the other day that in the sphere, this is 4/3 pi r cubed. So it's going to be 4/3 pi, and our radius is going to be, now I'm interpreting this 15.6 as representing the diameter. So just remember, please, that the radius is going to be half of that. Okay, so it should be 7.8, and we're going to cube that. This question did say round to the nearest tenth, or all round to the nearest tenth. So let's do it as... I'll do alpha y equals, we'll do 4/3, we're going to plug the pi in, and then we have 7.8 caret 3, and I should probably delete that box so I don't get an error, and we're looking at about 1987.8. And that would be cubic inches. The volume of the pyramid, this one had the third, 1/3 capital BH. So we have to find the area of the base. Well, keep in mind that the area of the rectangle would be 11 times 11, which would be 121. So that's going to go in for the area of the base, and then the height of the pyramid is going to be 12. Okay? So it's going to be alpha y equals, we'll do 1/3. Okay, we have 121 times 12, and that should be 484 cubic centimeters. The cylinder was pi r squared height. So that's going to be pi, my radius is 8. I'm going to square that. The height of the cylinder is 7. All right, so that's going to be pi 8 squared times 7. Okay, that should be 1407.4. That's going to be cubic kilometers. And then finally we have a cone, and the volume of the cone, that was a third of the cylinder. So that was 1/3 pi r squared h. So that's 1/3 pi. I'm going to say the radius is 9 because it looks like the diameter is 18 and then the height is 18. All right, so I'll do 1/3. I'm going to plug the pi in. I'm going to do 9 squared times 18. And I'll say that's going to be 1,526.8. All right, so we had a little bit of practice there with the solids, Cavalier's principle, and please look over the GeoGebra applets on the cross sections. All right, hope all is well. Talk to you soon.